Добрый день. Олег Карлович, это вы сейчас демонстрировали экран?
Да, это Гоша.
Да, это Гоша.
Да, здравствуйте.
Здравствуйте.
У меня какие-то смешные проблемы, которых не было.
Да,
То
давайте
есть,
попробуем решить, пока есть
когда
время, не
я
мешаем.
включаю свой экран, то я не вижу никого из присутствующих.
Это просто то, что у всех выключено видео. В этом проблема. Ничего страшного в этом нету. Я могу включить видео, вы будете меня видеть сбоку.
Ну, хотя бы, а то как-то в пустой
Это
экран
из-за того,
говорить.
я понимаю, да. Это после того, что видео выключено, обычно это приводит к тому, что давайте проверим. Я так вот на это смотрю, мне такое ощущение, что именно с этим делом было связано.
Ну, давайте я включу тогда свой...
И
так,
видите, что я зеваю. Может, из-за этого я выключаю экран, потому что тут у нас позднее вечер, уже 10 часов вечера в
ага.
Китае. Вот.
Сейчас,
Поэтому,
значит, я должен включить демонстрацию.
да.
Ага. Вот я
Здравствуйте, Олег
Теперь,
Карлович.
теперь меня
вот.
видно?
Ну, сейчас я
Сбоку меня
эм,
должно быть видно. Может,
вижу Диму
глядываете.
Гуревича. Сейчас вас
Вот.
сейчас
Да,
минутку, да?
я вот говорю, обычно, когда говорится, экран активируется. Я вас
Ага.
вижу, например, сбоку от экрана вашего.
Да. Сейчас я попробую
Вот сейчас
включить.
Саша. Я вижу Сашу Жеглова.
Здравствуйте, Олег
Сбоку от...
Карлович.
Здравствуйте, здравствуйте. Так, вот я запустил экран в свернутом виде, а на весь
Да.
экран, может, не стоит его запускать даже.
Как хотите, как хотите. В принципе, все видно.
Ага,
У нас несколько человек говорят по-английски, как
я понял.
минимум Хуго, это Сашин аспирант китайский. Он точно говорит по-английски.
Мгм.
Остальные вроде бы русскоговорящие, даже Варант вот довольно хорошо понимает русский, как я понимаю. Вот. Ну, я не знаю.
Отзирать
Саш,
подсоединиться, Гош?
Ну, я могу и
Нет,
по-английски.
Вераня практически до этого время идет преподавание, он сейчас там, по-моему, зашивается. Он
А,
никогда, он мог присоединяться. Ну, может, попозже присоединиться.
Окей, я могу по-английски, нет проблем, в общем.
Саш,
Скажите, как лучше?
что скажешь, Саша?
ну, исходя из того, что здесь есть англоговорящие, то, наверное, лучше по-английски, да.
Хорошо, договорились.
Ну, как бы, я не знаю, если будет один Дзюнху, может быть, можно и по-русски, если у вас в слайде на английском написано.
Да. Если англоговорящие товарищи отключатся, то вы мне дайте знать, я перейду на русский.
Пока практически
Хорошо,
все, кто
да,
в
хорошо.
Джинху, у нас русскоговорящие, я смотрю.
Мгм.
Все
Ну, пока
присутствующие.
да, но дело в том, что еще могут набежать, еще, так сказать. Обычно у
Могут.
нас люди минут на 5 приходят позже, то есть не ровно в 5, а там начинаем в 5 минут шестого, где-то так.
Ну, хорошо.
Я бы сказал, не ровно в 10 по-китайски.
Ну
Тогда
да,
я
да, да.
возьму паузу на несколько минут.
Да, конечно.
Хорошо. Мгм.
Окей?
Да.
Ой, извини, Саша, я что-то зеваю. А, Давайте спросим коллег, может, кто-то захочет сделать доклад. У нас пока, молодые люди, у нас пока в основном свободные места для докладов в ноябре. Практически весь ноябрь, кроме 21-го, у нас не занят. Если кто-то хочет, вот, пожалуйста, дайте знать. Может, ты, Саша, Дзюнху спросишь? Саша?
Так, может, ты что-то спрашивал вроде, нет?
Я спросил, я предложил всем сделать доклад. Я просто не знаю, у меня в ноябре все слоты свободны, кроме
Ага.
21-го. Вот.
Как мне еще избавиться вот от этой штуки сверху, которая мешает?
Ух, это
М,
какая у вас система?
А?
Я просто не знаю, какая это у вас система? В принципе, где-то должна быть такая опция, не знаю, по-моему, в просмотр.
Ну, вот
Я
тут
просто...
есть скрыть перемещаемые элементы управления конференцией.
Ой, нет, что-то другое.
Она
Посмотрите,
исчезает тогда.
у вас открыт по файл просмотр. Да, вот у вас это самое. Сейчас у вас открыт, как это называется, Adobe Reader. Откройте у него менюшку просмотр.
Так, и что?
Сейчас
Нет, эта штука, это не от...
полноэкранный режим нажмите пока.
Что?
Нажмите полноэкранный режим.
Это, конечно. Ну, тогда я перестану вас видеть. Нет,
Не знаю, не уверен, что вы перестанете нас видеть.
нет, это не то.
Не то? Я
Да.
уже вас вижу.
Хорошо.
Я
Я попробую отключить дополнительные элементы управления, но тогда, может быть, мне придется перезайти. Я не знаю.
попробуйте, хорошо.
Вот оно... Нет, все хорошо вроде бы. Нет, все нормально.
В Zoom есть какие-то опции, которые я никогда не использую.
Мгм.
Вот. Поэтому я не могу дать полноценный комментарий.
Вот, хорошо. Отлично.
Okay, I think we can start right now, right?
Yes, I think it's time to start.
Oh, Jiran has joined us. So there are two Chinese students, in fact, and this means that, yeah, probably better to speak English today. Okay. Oleg Karlovich, so let me introduce our speaker today. This is Oleg Karlovich Sheinman from Steklov Mathematical Institute and Independent University, and he's going to talk about the separation of variables for Hitchin systems. And okay, let's listen to this talk.
Okay. Thank you. First of all, thanks to organizers for the invitation. And I was told that I should be oriented to student level. For this reason, I will start with quite elementary things.
Yes.
Invariance of classical Lie groups. It's something which is familiar to everyone from the course of linear algebra. Let G be a classical simple or reductive Lie group.
Олег Карлович, извините, пожалуйста. Здесь какое-то эхо. То ли у кого-то включен звук и колонка. Может быть, дело в этом.
Но
Наверное,
не у
надо
меня.
просто у кого-то... У вас, да?
Нет, у меня колонки нет. У меня... Ну, а звук у меня должен быть включен, по идее.
That's Eins. Eins. Can you please? Oh, yeah, okay. Thanks.
Окей, yes.
Should
Я
I
думаю,
go
теперь
on?
будет нормально. Мгм.
Okay, I go on, okay? Let G be a classical simple or reductive Lie group, and frac G is its Lie algebra. Then let R stay for characteristic polynomial of a generic element L from the Lie algebra. This is just formal, just formally how it looks. Rg of L are just coefficients of characteristic polynomial. What? there are some talks in Zoom. I don't.
Дмитрий Ильич задает вопрос. Дмитрий Ильич, вас очень плохо слышно.
Okay. What is L as a matrix? So the algebra G is a matrix algebra.
Yes, it's written that it's classical. It's classical, and L is realized just as a matrix of size D. Yeah, it's
Okay.
written. Okay, good. And R, G are polynomials of entries of the matrix L. N is equal to rank of G. Now, examples. For G equal to GLN, R is just a polynomial containing all degrees, all powers of lambda. For symplectic group, R only contains even powers. For orthogonal group of odd size, the polynomial is reducible, but we just neglect this common multiplier lambda, and what is in the brackets is the same as the characteristic polynomial for symplectic group.
I'm sorry, I'm looking at the formula for SO2n plus 1, and it makes me a little bit, dizzy. I thought I used to believe that the free term in the characteristic polynomial is always equal to the determinant of the matrix. And it seems that there is no determinant of the matrix in this expression.
For odd dimension, the determinant is equal to 0. This is the point.
Oh, that's not the group. That's Lie algebra.
Yeah. That's algebra.
Yes.
Sorry, because you write SO capital. Yeah, sorry.
Okay, but
yeah, sorry for this. Definitely, yeah. That was just my.
Well, and finally, for orthogonal group or for Lie algebra of skew symmetric matrices of even size, the free term is just a full square q to power 2, where q is a Pfaffian of the matrix A. Okay, so by the form of characteristic polynomial, we can judge with which Lie algebra we actually work. The set of degrees of lambda in characteristic polynomials is d1 and so on dn determines the corresponding Lie algebra up to duality. What do I mean? The groups SP and SO 2n plus 1 are dual, and if we don't pay attention to common factor lambda for SO 2n plus 1, then characteristic polynomials are the same. This is what I mean when I tell that the set of degrees determines G up to duality. Okay, good. Now let's invent a hyperelliptic curve whose affine part is given by the equation y squared is equal to p 2g plus 1 of x, where p 2g plus 1 is a polynomial of x of degree to G plus 1. And choose, fix the divisor, which is equal to infinity with multiplicity to G minus 1, where, okay, G is already defined. And let's consider the coefficients of the characteristic polynomials to be elements of the space O of minus dj by d. Okay, these are meromorphic functions on this hyperelliptic surface, which have poles at infinity. The only pole at infinity of multiplicity not more than 2 by G minus 1. Okay?
Sorry, what is the characteristic polynomial? I don't quite understand. Of what matrix? Of what?
We had characteristic polynomials.
Yeah.
Right?
Yeah.
Forget about matrices. Now forget about matrices.
So we forget about matrices and we forget about characteristic polynomials at the same time, because when there is no matrix, no characteristic polynomial, nothing to characterize.
Let's forget about the matrix L, and consider these 4 types of polynomials.
Okay.
In order to distinguish these polynomials from the C of all polynomials, let me call them characteristic polynomials. Okay. Now, these polynomials have...
okay, just one moment, one more moment. So in this general point of view, from this point of view, what are coefficients of these polynomials? Just arbitrary number.
At this slide, which is now on the screen,
yeah, that's for sure.
Coefficients are not specified, but on the next slide, I am specifying the coefficients. Let them be meromorphic functions on hyperelliptic Riemann surface. Well,
any arbitrary functions?
No. Functions R with index G belongs to the space of meromorphic functions which have the only pole at infinity of order not more than 2G minus 1. Well,
so we forget about
DG. Dot DG.
Sorry?
Multiplied by DG. There is also the number DG here. So the pole is not more than...
Okay, okay, yes, multiplied by DG.
Yeah.
Okay, thank you. Thank you. Well, so our characteristic polynomials became polynomials with coefficients in the ring of meromorphic functions of given with given analytic conditions at infinity. Okay.
Mm-hmm.
Well, now we can point out a natural base in this space O. I will omit words O of minus dj by d and say just O. Okay, so we can easily point out a base in this space O. This base consists of powers of x from powers of x from 0 to dj by g minus 1, and powers of x multiplied by 1, where powers of x again run from 0 to what's written in the last monomial. Okay. As soon as we know the base, we can just write down an arbitrary element of this space O of meromorphic functions. It has this form, which I point out now, where H with 3 indices, 2 lower indices and 1 upper index, are coefficients, now complex coefficients. And let me plug these expressions for every g in the characteristic polynomial. So our characteristic polynomial becomes a polynomial from lambda x, y, and h. Let me recall, it was just polynomial. It was just a polynomial of lambda, but we plug r, which depends on x, y, with coefficients h, and we have these polynomials now as polynomials of 3 variables and parameters h. So we have equation. Let's write down the equation. Oh, sorry. Let's write down equation. 2 equations. Just defined r is equal to 0, and the equation of the hyperelliptic of original hyperelliptic curve. These 2 algebraic equations define a curve in C3. Well,
so it's in C3, x, y, and lambda, right?
Yes,
okay.
Yes, in C3. We projectivize this curve, and what we obtain call spectral curve. It's just a curve, but in order to distinguish it between all other curves, let me call it spectral. Okay. This is what I call spectral curve. Now, I would
Oleg
like...
Karlovich, one question.
No.
Is it important to take a hyperelliptic curve?
No, it is. No, it is not. But in order to make separation of variables effective, we should start with a certain class of curves. We cannot start just with a general curve. Yeah? Then, if so, we will not obtain any explicit answer in the end. By answer, I mean, for example, an explicit expression for Hitchin trajectories and so on. We can take hyperelliptic curves, or, for example, trigonal curves, or what Buchstaber and Sklyanin called NS curves, and so on. But all the machinery for the moment is developed for hyperelliptic curves.
Thank you.
Well, so what I have done to this moment, I just defined a curve, which I, for the reason which know only doesn't know anyone except for me, I call spectral curve. Okay, good. Now I would like to define Hitchin system. So if I have a curve, one of most natural ways to give this curve is just to point out the points. Points it passes through. Okay. My curve has this number has h how to say not yet determined coefficients, where h is equal for simple groups. H is equal to the dimension of the group or the corresponding Lie algebra by g-1, where g is the genus of the base curve.
So this is the number of points I need to pick to restore the curve, right?
Yeah, it's first of all the whole number of coefficients h when g runs from 0 to d, okay, to the dimension of the matrix.
So roughly in every point determines one coefficient, right? Of coefficient is equal to the number of coefficients.
Not really. 1 point doesn't determine any coefficient. But
here you say that number of points is equal to the number of coefficients.
Yeah. And here in this proposition, the number of coefficients is counted for simple groups.
The definition of H is the number of points you need to determine the curve in a unique way, right?
Yeah.
The definition of H. And then in the proof, you begin with not H is equal to the number of points, but H is equal to the number of coefficients. And I don't see why it is the same.
You will see. You will see just in a minute. Okay. Okay. So look at the last line. Yeah. We just plug the point with number I into the equation of the curve, and we have h exactly h. Okay, the number of equation on h is equal to the number of points. To the number of points we give. Okay.
Well, that's what I say. Every new point determines one coefficient, more or less. So
it's not true. It's not true. But the collection of points determines collection of coefficients.
Okay. So how do you prove that the number of coefficients is equal to the number of points?
Let me just remember your question until the end of this slide, okay? Only until the end of this slide. So here in this proposition, I counted the number of coefficients. Okay. Now I would like to define the phase space of the. I would like to define the system. Hitchin system, I must to define the phase space, Poisson bracket, and Hamiltonians. By phase space, I take the triple, a point of the phase space consists of H triples lambda I, xi, yi, related by the equation of the hyperelliptic curve. So far, H is the number of, H is the number of points. Here, H is a number, certain number of points of certain number of points of the spectral curve. Well, on these sets, I define a Poisson bracket just by definition. Lambda I with xj is either 0 or yi, and all other brackets are equal to 0. Hamiltonians are defined from the system of linear equations, which express the fact that spectral curve passes through these H points. So I took H points. I have H unknown coefficients. By plugging these H points into the equation of spectral curve, I obtain the system of linear equations, system of H linear equations on H unknowns. In general, I can find out these unknowns via the coordinates of points. It's by the way, it's non-homogeneous system of linear equations because its right hand side consists of this lambda I to d. Gosha, are there any question in remainder? And is there any question? Huh?
You obtain linear equations. That's more or less clear. I just don't quite understand why these equations are, linearly independent. I mean, yeah.
It depends. It's just condition of generic position. It depends on the choice of these triples. Okay?
Yeah, I understand that actually the number of coefficients we need to determine is equal to the number of equations we have to we need to meet, and each equation just one point. That's precisely what I said. That each point determines one coefficient, more or less. Yeah, that's just...
okay.
Okay, but that's okay. I mean, that's what I mean, and now we actually understand each other.
Well, maybe the following comment can help. What I'm going to do is to define the Hitchin system on the open dense subset of conventional Hitchin system. and conventional Hitchin phase space. Okay, not okay. Well, so phase space is defined, Poisson bracket is defined, and Hamiltonians are defined.
Space is the configuration space of points, right? Okay.
Sorry?
Okay. Yeah, yes, I just looked for the definition. Phase space is equal to the configuration space of points.
In your microphone is again turned on, and the echo sounds. Can you please turn off your microphone?
Well, so from this system of linear, let me tell that for orthogonal group of even dimension, this system is not linear but quadratic. But let me just skip all comments on this subject. Okay. Let's regard to our group G as to one of three groups Gln SP to n as O to n plus 1, just for simplicity. Well, from this system of linear equations, we can find out this H with three indices and express them via the set of xi, yi, lambda I. And also observe that yi and xi are related by this equation. And basically, we have two parameters, xi and lambda I here. Now, I would like to explain why this system is why we obtained an integrable system. The point is the following. Let's forget for a moment about three index enumeration let's label all our variables just through by one index from 1 to h. Good. Then there is a following statement. If we have the system of equations of such form, which is pointed out now at the screen, where f, j are, or fi, sorry, are quite arbitrary functions. For example, smooth, or analytic, or something like that, not necessarily linear, and the peculiarity of this system of equation is the following: every equation contains only one pair of variables lambda I, xi. So the equation with number I contains all h's, but only one pair of variables lambda I, xi. Consider a Poisson bracket of the following form. the characteristic property of this form is the following. This is a combination of Poisson brackets in every pair of variables x lambda with coefficients which are functions of namely z x and z lambda. Then there is the following statement takes place, that for under a certain assumption of non-degeneracy, functions h as functions of lambda and x Poisson compute with respect to such Poisson bracket.
Doesn't it depend on the choice of HK, small HK?
Sorry.
I mean, here at line 1, the formula 1, you have HK, small HK as the parameter of the Poisson bracket.
Oh, small HK has nothing to do with H, which appears.
Yeah, but so I mean, this statement that this HI and HJ capital commute for all I and J, if this condition holds, doesn't depend on the choice of HK small.
Yes, doesn't depend. That's true. That's true. Which I will actually show that HK can be that H, I, and J commute with respect to every such degenerate Poisson bracket, and then we can just take their combination if we want. Well, is the statement clear or not?
Yes, it is.
Are there questions at this point? Again, every system of functional equations of this special form, the speciality, is the following: every equation contains only its own pair of lambda I and xi. Every such system of linear equations defines an integrable system with Hamiltonians which are obtained by resolving this system of equations with respect to H, and with Poisson bracket of this form. Well, the proof is that simple that I will give it here. Let's take the equation of the system with number I, and also fix certain k. Assume that I is not equal to k. So I mean, just how to say, как сказать, вычеркнуть. Just drop out the equation number k from our system, and what we will have, what is in the remainder, we differentiate first in lambda k and second in hk. Then here we have h minus 1, h small h minus 1 equations here and h minus 1 equations here. We have two linear systems of equations. First one on the vector, on this vector, dh over d lambda, and the second one for this vector, dh over dk. But for my maximal rank condition, which I showed but not formulated, sorry, by this maximal rank condition, both systems, sorry. These two vectors satisfy to the same system because coefficients d phi I over d h over dh are the same here and here. This system has only one linear independent solution, because its rank, the rank of its matrix, is h minus 1. Hence, these two vectors are proportional, and hence all minors of second order constructed of elements of entries of this method of these vectors are equal to 0. But this means that the elementary Poisson bracket of hi and hj is equal to 0 for every I and for every pair I and j and a given k. Is it clear?
Yeah.
Or not? For this reason, every system given system given by this system of functional equations is integrable.
Mm-hmm.
Example, SL2. Then our set of points. Sorry. Our spectral curve is nothing. It's not written here, and sorry about that. But the equation of the spectral curve is just quadratic and has no first order term in lambda, because the trace of the matrix is equal to 0. So the characteristic equation consists of the square of lambda and certain quadratic polynomial of x. And additional equation related to the hyperelliptic curve, which I took of genus 2. Then we the only thing we must do is the following: to resolve the system of linear equations with three variables: h0, h1, h2. Well, and just by well-known formula, it's
That's what they call Kramer rule, right?
Yeah, just by Hammer rule, it's just the ratio. Every Hamiltonian is just the ratio of two determinants, where in the denominator we have Vandermonde determinant, and in the nominator, in the nominators, we have Vandermonde, where one of columns is replaced by the column of free terms. Well, and symplectic form is like this. It's like this. And which means that Poisson bracket is also very simple, and we can easily write down Hitchin equations in this case. It maybe sounds funny, but since let's say 1998, I guess 1998 till 2018, there was impossible, too hard to write down any Hitchin system explicitly. There was no explicit representation of Hitchin systems. There were for SL2, there were quite known works by Emma Privata and Van Gehman, and another one by Krzysztof Gawecki, the physicist, and SL2 Hitchin system was represented quite implicitly. And only in 2018, when I invented these coordinates xi lambda yi, it became possible to write down the Hitchin system really explicitly. And not only for SL2, but also for at least for all rank 2 Lie algebras, simple Lie algebras. Well, now let me continue with a method of generating functions. How to okay. Let me just start my way to an explicit explicit formula for Hitchin trajectories. The aim of method of generating functions is just one of basic methods of symplectic geometry, and in our setup, it can be formulated as follows. We would like to find coordinates phi, h coordinates phi 1 and so phi h, which are symplectically dual to h coordinates. I mean, the symplectic form has canonical canonical expression in these coordinates. But moreover, H's are integrals integrals of the system. Such coordinates which where omega has a canonical form are referred to as Darboux coordinates, but in my case, we have a bit more than just Darboux coordinates. We have such Darboux coordinates where half of coordinates are Hamiltonians. Motivation for that is easy. In such coordinates, Hamiltonian trajectories are just straight lines. Let Ti be a time parameter on ice Hitchin flow. Then all coordinates hi are constants, and all coordinates phi are ruled by Hamiltonian equations, which amounts to this easy linear equation. How to find out this coordinates phi? It's a deep classic, which goes back to Hamilton and Jacobi, and in contemporary form formulated by Vladimir Arnold. And the form I will use here, I should say in the most simple form is formulated by Sklyanin. The prescription is as follows. Phi can be found out as just derivative of a certain function s by h with the corresponding index. This function s has several names. It's called action, or among physicists it's called action. In symplectic geometry it's called generating function, where generating in sense of symplectic geometry is a function which somehow generates symplectic transformation. Nothing to do with power series. Well, and I will go on with the statement. Phi j is just such a derivative, where in our situation of separation of variables, s is a sum of function si. Every one of them depends on the parameter, on the local parameter, on the copy of the base curve with number I. I will explain this. And this parameter, it's better to call this parameter not local, but quasi-global. It can be computed, it can be defined via this integral. Observe that our phase space, let me return, our phase space is just symmetric product of h base curves of h hyperelliptic curves, which I refer to as base curves. So having a holomorphic differential dx over y on the base curve, we can define the following quasi-global coordinates. Quasi-global in the sense that its coordinates it's a coordinate in the open dense set. In the open dense set. And the I is nothing but this coordinate on the i's copy, on the copy number I of our symmetric product of base curves. So the function S is
Oleg Karlovich, sorry, what was gamma?
Gamma. I define local coordinate. Actually I had to write z of gamma. Okay, I define a local coordinate of the point gamma. Good?
Okay.
Sorry.
Okay.
Sorry. So our function S is just a sum of simple functions Si. Every one is the function of this quasi-global coordinate, quasi-global coordinate, and the function Si has to be found from the equation of the spectral curve, where lambda is replaced with this partial derivative. And I haven't written here x, y, I, y. I just replace them by this quasi-global coordinate. Good. So I express them via quasi-global coordinate and plugged into the equation. Now, this is just prescription. I'm not going to prove it. These are quite. It's sufficient to refer to Arnold's book and to famous Sklyanin's survey of 90s of last century. Good. Now let's derive this equation in lambda. It's written here. And express dsi over dzi via everything else. It will be just the ratio of this, just the ratio of this and this. Well, and just sum up, further on, sum up in I, and we obtain the expression of this derivative, which we need actually via equation of the spectral curve. dz can be replaced here by dx or by. Any question at this point?
So this is just the Hamilton Jacobi, I think, right? Nothing else. Just look. I see.
Gosha, you are too silent.
I mean, I can only see Hamilton Jacobi proposition here. I don't see anything to say.
It's not really. I skipped this. I just how to say, I just extracted what we need in our situation.
Yeah. So that's just a preliminary. That's what I was going to ask. It was not just the main result. It was just a preliminary work. Tells the brain the main result.
In some sense, it's already a result. You will see. So we expressed. Observe that we expressed this symplectically dual coordinates phi via such integrals. Okay.
Mm-hmm. So again, how
let me first formulate the theorem and then comment on the formulas over it. Return. Okay. Integrands. These integrants, or
show me
in other
the definition of SI. Somehow
the definition of
goes
SI.
Yeah.
SI is a solution. SI should be found from this equation. Is determined by this equation.
The previous slide again.
Huh?
I have a feeling I missed something in the previous slide. Can you show me the previous slide? Oh,
which previous?
No, this is I saw this. And next one. Next again. That's just example.
So,
yeah, I see. So just.
In the case of Gillian, sorry, I switch here. I switch here to the notation AN, BN, CN, but AN corresponds to Gillian, BN to SO 2n plus 1, and CN to SP to n. Well, so the statement is that the integrands form a base of holomorphic differential in the case of Gillian, and the base of holomorphic Prim differential for the systems B and Cn. Don't pay attention to A1 here, sorry. I told you, and we have seen at the very first slides, that for orthogonal and symplectic groups or Lie algebras, characteristic polynomial contains only even powers. For this reason, it is invariant. The spectral curve is invariant with respect to the involution lambda to minus lambda. And Prim differentials are differentials on the spectral curve, meromorphic differentials on the spectral curve, skew invariant with respect to this involution. So the statement is that for Gillian, it's a base of all holomorphic differentials, and for simple groups, integrands form a base of holomorphic Prim differentials. What is done here is the following. I return to the three-index enumeration of Hamiltonians and corresponding dual phi's, and just explicitly expressed phi's via lambda x and y from these relations. But what is important? It is important so far, as soon as integrands are basis holomorphic or Prim differentials, the transform from xy, yi, lambda y from this set to phi is nothing but Abel transform in case of GLN and Abel Prim transform in the case of simple classical groups. By definition, if integrands run over all holomorphic differential, this is called Abel transform. If they run or basis Prim differential, it's called Prim or Abel Prim transform. And the corresponding image in the case of Abel transform is called Jacobian, and of our spectral curve. And in the second case, in case of Prim differential, it's called Prim variety or Riemann of our spectral curve. And we have obtained that Hitchin trajectories are straight lines on the Jacobian or Riemann of the spectral curve.
It's some classical statement, I believe. I heard this.
It's basically statement by Hitchin, but here here I obtained it just by constructive methods.
Oh, I see. Yeah. So theoretically, when you I heard the general theory is that when you apply Abel transform, you obtain straight lines from the trajectories. And here it's formulas. Yeah.
It can be obtained by several methods. Just for example, by inverse spectral method, or by Hitchin's methods, and so on. But here I just in order to make my talk self-consistent, I obtained it just by methods of separation of variables. Well, why they are straight lines? It follows from this formula for phi, how phi evaluates. How phi change with time. It's just straight line.
Oleg Karlovich, and what's about the dn case? What happens? What happens for dn case?
For dn case, at least this statement is no difference. With this statement, there is no difference. There are problems with explicit formulas for Hamiltonians and for theta formula for solution, which I hope talk to it here, but we will see whether I have enough time.
Okay. There's some hidden problems.
Sorry?
These are some problems.
Okay, my former student, Polina Borisova, said everything explicitly for SO4, but for SO6 and more, it's already a transcendental problem.
Oh, interesting.
In some sense, transcendental.
You said that it was explicit and now it's transcendental. I see some control.
Yeah, it sounds a little bit strange, right? Why dn case is so different?
It's algebraic problem. That has not any effective solution. The reason is the same as for equation of fifth degree and more.
So you cannot just integrate something.
Yeah,
in
we cannot express it in radicals and so on.
Yeah, so integration cannot be done in elementary functions, I see.
Yeah. Okay. We obtain that Hitchin trajectories are straight lines on the corresponding abelian variety. But what we would like to have is the expression for Hitchin trajectories in original coordinates x, y, yi, lambda I. As I said, the transformation from these original coordinates to phi is Abel transformation or Abel Prim transformation. So, if we could reverse Abel transform or Prim transform, we could just take this straight line on the Abelian variety and send it back to the phase space by inversion of Abel transform or Prim transform. For Ln, it's possible, but I will explain that for simple groups, I see certain abstraction. In principle, to reverse the Abel transform, it's a classical problem called Jacobi or Jacobi inversion problem. And in principle, it can be resolved by means of Riemann's theorem. We must take theta, the theta function, the Riemann theta function, or which is the same, the theta function of Jacobi. Then by Riemann's theorem, the preimage of any point phi of the Jacobian is given by the set of zeros of the following function. We just take a point of spectral curve, take Abel transform from this point, take phi, which we can send back to the symmetric power of curves, and take certain vector k called vector of Riemann constants, which is constant, and I will not comment on it at all. So we plug this combination in theta function and look for zeros of the obtained function f.
So theta of AP minus of phi minus this combination is the inverse of the Jacobi transformation, right? Of Abel transform.
No.
Right.
Sorry. Zeros of this function gives inverse image of phi.
Okay.
We take phi, and all this we take phi. Actually, only phi is of importance. Plug it here. Look for zeros of this function and obtain the inverse image of phi.
These zeros can be multiple points, so it seems that one point can go to several. Is it some kind of?
But sorry, phi belongs to H-dimensional variety, and we exactly obtain H zeros in a general point. We exactly obtain H zeros of
Kind of
function.
H. So the Jacobi this Abel transform is just H. is just kind covering space with H branches, right?
Gosha, I'm not really hear everything.
Я просто имею в виду, что если мы возьмем Абелеву, преобразование Абеля, то имеется в виду, что в одной точке справа будет 6 прообразов. Вы получаете их все как нули этого преобразования.
Не совсем так. Мы... So, no. We have here H points. And we have...
1 point.
Huh?
Ah, no, then not they go... Oh, I see.
We have H points of the spectral curve. And we had symmetric, and here is summation in I.
I see.
Or here, if you like, it's symmetric expression of H points.
It's actually symmetric. It's a map. So the Abel transform is a map of symmetric power to this Jacobian, the Jacobian.
Yeah, Jacobian is rationally isomorphic to the H symmetric power of the spectral curve.
And that's transform, actually, Jacobi transform. I see. Okay.
Well, but the Riemann theorem certainly gives solution of the problem only in principle. I will explain. Gives only in principle because we still should find out the zeros. How to do that? We still have not write any explicit expression for the inverse transform. Okay. I will comment on effective solution a little bit later, but now let me notice that for simple structure groups, even this solution in principle is not possible. It's not possible because for simple groups, the trajectories are straight lines on premiums. And if we would like to manage like in Riemann theorem, we should take theta function of the premium, or what's called prim theta function. But similar statement for prim theta function is quite different. In the case of Riemann theta function, the dimension of the Abelian variety was equal to the number of zeros of this function f. And this is why we were able to really reverse Abel transform. In the case of Prim varieties, the numbers of zeros of this function f of p is twice the dimension of the Prim variety. I refer here to the famous lecture notes, by Fay, theta functions on Riemann surfaces. And this makes a problem because in the original coordinates x, y, y, I, lambda y, the point of the phase space consists of h of the point. the point of the phase space consists of h points of the spectral curve. Then we go by direct transform. We are sent to h-dimensional Prim variety. But the inverse transform gives us twice h points, and there is no way to distinguish any h of them. Is the abstraction clear?
Yeah.
The abstraction, the nature. Sorry, the abstraction is due to the fact that Riemann theorem has different nature for Jacobians and Primians.
Mm-hmm.
Well, now about effective inversion. As I said, let me return to the previous slide. As I said, this transform, this direct transform, what is it doing? It to the sorry, to the non-ordered set of points of the spectral curve, it sends to Jacobian. Now I concentrate on the case JLN, and our Abelian variety is Jacobian. So this transform is symmetric with respect to xi with this tripole, with respect to the set of these triples. Well, and this means that if we would like to inverse the transform, we cannot hope to find out every point separately. We only can hope to find out symmetric functions of this set. I know this from the survey by Dubrovin of 1981, but I'm not really sure that this observation belongs to Dubrovin, that this idea belongs to Dubrovin. But conditionally, I would like to say that it's an observation by Dubrovin. Let me let's consider simplest symmetric functions of our points. It depends only on x coordinates of points. Y's are dependent. Sorry, Y's are dependent, and I will ignore them now. And if we know x coordinates x, we somehow can find out lambdas from the equation of the spectral curve. So I will focus on finding out of x1 and so on xh. Let's define the simplest symmetric functions, Newton polynomial from these quantities. Then we can give the following explicit formula for this function, for these functions. Is certain constant, which I don't comment, plus certain combination of differential operators, which are explicitly given, I explain it, which are explicitly given, applied to the logarithm of the theta function.
So what is what is partial d? D
What is
capital
partial d? Theta function depends on h arguments here.
Yeah.
And partial d is derivative in argument number I.
And why isn't it absorbed into dj, in the capital dj? I don't quite understand.
So, sorry. I think okay. For any set of integers of non-negative integers, we can write down such differential operator. There is no question. There is no question.
The question is why doesn't
explanation are these coefficients?
No. The question that was a very simple question. Why isn't it partial di absorbed into dj capital?
By actually by formal reason. We could do that.
So di is just
actually an honest answer is actually I don't remember. An honest answer is I don't remember. There is no principal abstraction. It can be done, but
okay, I see. It's just some tradition.
But
I think the formula will not.
For some reason, I didn't like it when I was writing this slide.
Because I think the formula will not be symmetric in that case, because we cannot write that the sum of indices is equal to j.
Oh, okay.
We just add it there.
Okay.
What is non-symmetric?
dj. We cannot just write down a symmetric formula in that case, because dj now is very symmetric. There's a sum of ji's is equal to j.
Okay, I understand. Yeah, okay. This is just the way to write the formula. Okay. I thought it was some different partial derivative along some other differential, some other coordinates. But yeah, in this case, it's just, makes some sense. Okay.
Well, so we just take sets of integers j satisfying this inequality, and just sum up this this expressions. Well, so kappa ij needs to be explained. Actually, everything is written except for what are phi I or phi s with an upper index in brackets. These are nothing but coefficients of expansions of holomorphic differentials, of basic holomorphic differentials in the neighborhood of infinity, and for this reason they are just known functions. You see,
what is AS of P? ASA looks like the Abel transform, right?
AS of P
Abel
A of P is the Abel transform,
Yeah,
and
what
A
is
is its coordinate number S.
Oh, so that's coordinate of Abel transform.
It's just integral of the corresponding holomorphic differential. Coefficients of this differential are exactly phi s to ls.
I also thought that Abel transform, you need to plug in points on your curve into the Abel transform, and here you plug in some polynomial, which makes it a little strange.
Sorry.
I mean, Abel map, well, the argument of Abel map, I thought that the arguments of Abel map were points. And here
an argument of Abel map may be, it depends. It may be just a point or maybe 3 points, maybe divisor of degree G. Any divisor in particular a point.
So it's just the PZ is divisor, right?
Here P is just a point. Here P is just a point close to infinity.
What is P of Z then? You just not familiar with this notation. P of Z.
P of Z. Okay, good.
Like polynomial for me. So
no. Z is okay, good. Z is a local coordinate on the spectral curve.
I see.
Near infinity.
Okay, I see. Yeah, now I understand.
P respectively is the point close to infinity.
Okay, I understand.
If you forget about this denominator and shift degree of Z by 1, you obtain the expansion of the corresponding holomorphic differential. After integration, Abel transform is just integral of holomorphic differential. There appears this denominator and shift of powers disappears.
I see. Thanks.
Okay, and this is an explicit formula by plugging the linear certain straight line on Jacobian, by plugging it into this relation, we just obtain symmetric functions of x's, of x1 and so on, xh, in terms of t. We just obtain the evolution of symmetric functions of the points of a point on Hitchin trajectory. This is in this sense we can find out Hitchin trajectories explicitly and no more. I guess this is a right point to finish my talk.
Yeah, it was pretty. How many slides did you miss? I just wonder.
Yes.
How many slides in remainder?
Yeah. There.
Okay. Proof of this formula and conventional and Hitchin systems in conventional setup and relation with that setup I just presented.
Okay. So
let's skip it because
definitely we don't have time to talk about this. Maybe we can continue. I'm sorry,
yes,
but
maybe yes. If you could give us another talk in November, you could explain us this inverse spectral method.
Because it's actually very interesting,
nice
and
for students.
I recently have some experience with systems on symmetric matrices. So here you work with matrices, just matrices in GLN, in SLN, and
Yeah,
also SLN and so on. But probably, I think you talked to Dimitri Alive. So we have some experience of working with symmetric matrices inside these spaces, and they have some special properties, and it is quite interesting whether similar constructions can be applied there and what they give. This is related to full symmetric Toda, and that's quite intriguing because their trajectories are also quite interesting and worth studying. Okay, so yeah, let us thank the speaker again for a wonderful presentation, and I hope that we'll still have time to discuss the remaining part of the slides, maybe something else. Are there any questions or comments from the audience?
I guess the audience is already.
Half asleep. I'm afraid that yeah, Varanta
No. They just thank you. I think the talk
Yeah,
was
they
very
just thanks.
clear, but of course, maybe it would be better to hear more details on the rest and also on the inverse spectral method.
Yeah, definitely.
If
Definitely.
you'll have time, then probably maybe you could explain this again.
Okay, it depends. I'm still not sure about my plans in November.
Yeah. Yeah.
So
Okay.
next time, Ian, when next time we meet, I hope your microphone will work. So yeah, that's actually another incentive for us to meet again, because Ian will have his microphone working at that time, and then he will be more active participant. Yeah, that's precisely what I said. Ian has questions, but he cannot ask them properly without his microphone. So next time we meet, he'll have his microphone on, and we can actually have a more fruitful discussion. Okay, so let us thank the speaker again for a wonderful presentation. Next time we will have a talk by Professor Magno from Angers. Yeah, I'll send the announcement, title, and abstract on weekend.
Олег Карлович, а вы можете прислать нам ваши слайды?
Да.
Полную версию. Потому что там, конечно, да.
Конечно.
Ну,
Конечно,
должен
очень
сказать, конечно, что все равно некоторая мистерия по поводу вот именно случая ДН остается. Так вроде кажется, ну, как бы что нам
Почему?
мешает.
Так тут maybe we switch to English.
Well,
there is certainly there is a mystery, because my personal experience says that everything which can be done for GLN should be done, should be possible also for simple classical groups. But here we observe some mystery. For me, this is a mystery.
I have same experience. I've had same experience recently, because we have some statement about the structure of universal enveloping algebras in the case of A series of GLN. But when we try to transfer it naively to other series, it fails. It fails in certain, not in evident way. It's actually very unexpected. Yeah.
I see.
Okay, so thank you, and I hope we can actually meet again. We actually, Boris Karlovich, we have free almost every Tuesday in November, except for 21st of November. Every other all the other Tuesdays are free for you to choose if you can continue this talk, if you would like to tell us about the proof and some more details. We'll be more than happy to have you our guest again.
Okay, thank you, and sorry that I was so slow.
No, 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 no. It was good that you were so slow, actually. You see, it is the purpose of this seminar to give people time and means to understand. And when the speaker is very fast, who can follow him?
Yes, yes, right.
Yeah,
Especially
so
it was beautiful for students. Yeah, one of aim of our seminar is that students could also give here talks on their topics, and sometimes this happens, not so often, unfortunately, but however.
Yeah.
And yeah, since we all try to study some basic things like spectral curves, integrable systems, all these things are very interesting.
No.
Sorry?
Information quantization too.
Yes. No, I mean related to your theme. Yeah, I now mentioned all these things that are related to Oleg Karlovich, talk. Yeah. So, but by that reason, it's important, and it was also useful for me because I just want to understand this mystery, why everything works good for JLN and doesn't work. Yes, yeah.
Okay.
Thank
Okay.
you.
Yeah.
Okay.
Okay.
Yeah. Okay.
Thank you.
Bye
Thank
bye.
you.
Thank you.
Bye bye.
Yeah. See everybody next Tuesday. Okay. Bye.
Oh. No, no. Somehow I'm not able to switch off.
Надо просто выйти. Там справа внизу кнопка выйти есть.
У меня ничего нет.
А справа внизу там есть выйти. Нету? Ну, можно, наверное, прекратить демонстрацию экрана просто.
Да, может быть.
Сейчас.
О, спасибо. Все, теперь есть.
Вот, все, да.
Все хорошо.
До свидания. Спасибо.